Hi everyone, my name is Neha Kadam and this is the first lecture on Introduction to Electronic Communications. Now what is electronic communications? Electronics communication means transfer of information electronically by wire, radio, electromagnetic, fiber optic, cables, etc. Electronic communication system consists of a transmitter, a communication channel or medium, and a receiver. So we can say that communication is basically defined as the transfer of meaningful information from one point to another. And communication system here you can see in the picture consists of three important key elements, which is transmitter, communication channel, and a receiver. In electronics communication system, the information is referred to as a message, which is transferred through this communication channel. So here the message is in the form of electronic signal and it is fed from a transmitter, and it travels from transmitter to the communication channel and from here to the receiver. So along the way you can see here there is a noise which is added in the communication channel and is transformed to the receiver side. So this noise is the general term applied to any phenomena that degrades or interferes with the transmitted information. Now, some of the good examples for electronic communication would be TV broadcast or listening to radio. So these are most visible application of electronic communication. And in the past, if you remember, analog TVs, they used to be very sophisticated technology based, but nowadays we have high definition TV which uses complex digital and software technology together along with advanced analog circuit techniques. Another example of electronic communication would be telephone. Your voice may be sent using many different technologies. Analog transmission carries your conversation to the central office. From there, the signal is converted to digital, and then that digital signal is sent through maybe fiber optics cables. So the process is reversed at the destination, and during the process, your conversation may also travel by radio wave to and from a satellite. And in case of a cellular telephones, transmit and receive voice signals as stream of digital data over ultra high frequency radio frequency carrier signals. There are many more examples like a remote car which uses a radio transmitter. In that, a small microprocessor encodes digital data into the transmitted radio wave to represent the user's command. Another example of electronic communication would be commercial flights, which uses numerous types of communications to ensure flight safety. Uh, in the airplane, they mostly uses GPS technology for accurate navigation. So these radio and associated technologies are a big part of electronic communication. But it is not the only thing. Electronic technicians may work with a wide variety of systems, including radar, satellites, telephone, and computer telecommunications. Now, moving on to the next slide. Now we are going to learn about the communication channels. So the communication channels is the medium by which the electronic signal is sent from one place to another. Many different types of media are used in communication system, including wire conductors, fiber optic cables, and free space. So here the communication channel, it has a medium, and if we talk about the wire conductor, then it is the simplest form of medium, and it may be simply be a pair of wires that carry a voice signal from microphone to a headset. It can be coaxial cable such as that used to carry TV signals, or maybe twisted pair cables can be used, which you can commonly find in the local area network. And then we have optical medium, which is your fiber optics, which uses light pipe that carries the message on a light wave. These are widely used to carry long distance calls and all internet communications. In audio or video signals, it can be used to carry the amplitude of lights. And then we have free space. So free space means wireless communication here we are talking about. So intelligent signals are converted to electric and magnetic fields that propagate nearly instantaneously through space over a long distance. And for that, the common example would be your radio. And there are other types of mediums also present. For example, in sonar, water is used as a medium, and passive sonar, it basically listens for underground sounds with sensitive hydrophones. Now moving on to the next slide. Now here we are going to learn about types of communications. Under that, first we have one-way or two-way transmissions. One-way is called your simplex, or two-way is called your full duplex or half duplex. And there is another type of communication which is there, analog or digital signals. So let's begin with simplex. Simplex is the simplest way in which electronic communication is conducted. In one-way communications normally referred to as simplex communication. So for that, the example would be radio and TV broadcasting, or remotely controlled vehicle like toy car or drone. And here one such example is given where here you can see an antenna is there, and it is taking up the signal from this TV transmitter. So this is an example of a TV broadcasting. Now moving on to the next slide. So here we have full duplex, and it means the bulk of electronic communication is two-way or duplex communication. Typical duplex applications are shown here, and this diagram shows the full duplex communication, where you can see there are two phones are there and they are connected to each other, and two-way communication is taking place here. So people communicating with one another over the telephone can talk and listen simultaneously. Now next is half duplex, and it is the form of two-way communication in which only one party transmits at a time, is known as half duplex communications. So this is the form of two-way communication. You can see here in this example, we have a speaker and we have a microphone over here connected to this antenna, or you can say transmitter, and then from here it is transmitted to here, and then we have another speaker or microphone. So so for example, if you speak on the microphone and it is received over here, then you can listen to the information from this speaker. And similarly, if you send the information to this microphone, and then that information is basically sent over this, and through this receiver you can listen to that information through this speaker. So in this figure, we understand that at one time only one information is being sent. Two-way communication is not being done in this one. And for this, the example would be military radio system, fire police, aircraft, family radio, amateur radio communications, and they all uses half duplex. Now here next is our analog signals. Analog signal is a smoothly and continuously varying voltage or current, and for that example is given over here. You can see this is a sine wave tone, and this is the voice. And here we have taken the example of video TV signal, how it looks like. You can see the sync pulse, and these represent the light variation along one scan line of video. And again, this is the sync pulse. So here you see the example of analog. signals. Now moving on to the next one. Digital signals. So digital signals, in contrast to analog signals, do not vary continuously but change in steps or in discrete increments. And for that, the example is given over here. Mark space, and this is the mark space and mark, and this mark represents this dot, the signal, and here this is another signal. So here at the output side, you can see first of all, this is basically an example of a telegraph, and for example, let's assume this is a Morse code, and this is a continuous wave code which is given, and at the output you will get something like this between 0 and 5 volts, and the signal will be in the form of 0 1. So this represents the digital signals which work in on and off condition. Now comes the parts of radio systems. So these are the simplest key elements of a radio system which you see on the slides. So here, starting from this microphone, this is the microphone which converts the pressure or variation in a sound wave into an electrical energy. So this microphone, if we talk about, it has a thin plastic or a paper cone connected to a coil of wire. And for that, first of all, I'll give you the example. I'll go moving on to the next slide, and we'll come back to the previous slide again. So here you see this is an example of a microphone which has a thin plastic or or paper cone connected to a coil of wire, and this coil is placed within the field of a permanent magnet. So this is the coil I'm talking about. So when sound strikes the cone, it vibrates, moving the coil back and forth within the magnetic field. Thus a voltage is generated in the coil, and that is a copy of the sound wave that entered the microphone. So most microphone, they produces about 10 microvolts at a power levels of about 40 microwatt. Some voltage and power, so amplification, so for that amplification is basically needed so that the higher amplitude of signal can be transferred. And to amplify that, what we use the power amplifiers. Now I'll go back to the previous slide. So here you see we talked about the microphone and how the voltage is generated, and then it is sent to the power amplifiers, and these power amplifiers helps in increasing the magnitude of the signal, and it can range from few milliwatts to 1000 watts, and then it is sent to the transmit antenna, and from there transmitting antenna next converts the amplified signal into a new form of energy, and that is capable of traveling through the space. So here you can see we have a space between transmit antenna and the receiver antenna. So the information travels through the space, and this new energy which travels through the space is basically called electromagnetic energy or a radio wave. And this electromagnetic energy is basically two types, electric and magnetic, and the energy from the radio wave it moves towards from the transmitting antenna at the speed of light, which is 3 cross 10 raised to power 8 miles meter per second. So it spreads out, the energy is basically spreads out over the space, much like an inflating balloon, but the time it reaches receiver's antenna, it is very little. So here radio receivers typically receives picowatts or maybe very like to the power of 1 to the power of 10 raised to 1 cross 10 raised to power of negative 15 watts of energy from its antenna. So you can imagine that. And thus that's why we have this voltage amplifier connected here, and then a power amplifier connected here to basically increase the magnitude of that signals, and then through the loudspeaker another transducer is there which converts the electrical signal to the sound signal, and that is how we are able to listen to the sound from a microphone. Now here the system which I have shown here is simple, but it is impractical radio system. Why do you think that this is impractical? We are going to learn that in the next coming slide. So here are the two reasons for that. First is a long antenna. So directly transmitting audio signals in the 20 hertz to 20 kilohertz would result in a very long wavelengths. The wavelength of a 1 kilohertz signal in free space is 300 kilometer, which would require very large antennas to radiate effectively. So here we see the problem that it would be nearly impossible to build a transmitting antenna to work with this system. And the second problem here is interstation interference. If two or more stations transmitted at the same time, they would clash because they would be sharing the same frequencies. So these two problems we are going to discuss in detail in the next coming slides. But before that, we need to know what is wavelength. So here it says what is a radio wave. It is basically a wavelength which is refers to the distance a radio wave travels in one cycle. So here you can see how the wavelength has been represented, and it can be given by this formula. Lambda is equals to V by F, where this lambda represents the wavelength and V is the speed of light and F stands for frequency. Now coming back to the problem first, which is mentioned over here, that we might need a long antenna. To just discuss this, we need to understand that in order to be efficient, radio transmitting antennas needs to be at least 1/4 of a wavelength long. Shorter antennas can be made to work, but they don't radiate energy very well. To illustrate this, we'll take an example of a 1 kilohertz frequency. Let's say the frequency is 1 kilohertz, and we already know V is equals to 3 into 10 raised to the power 8 meter per second. So the wavelength will be, in this case, wavelength will be given by V by F, and if you do the math, then you will get around 300 kilometer. So which means that your wavelength should be 300 kilometer, and now your antenna which you want to make needs to be 1/4 of this distance. So 1/4 of this will be 1/4 by 4, and this will be your 75 kilometer. Or we can say that 46.6 miles. So you can see that we need this much length of antenna long if in case if we are working on a frequency of 1 kilohertz. So the length is too long in this case. Now the question is how to reduce the length of the antenna. To do that, we will understand from this formula which says lambda is equals to V by F. So what if we increase the frequency? Let's say if we increase this frequency, then what will happen? The wavelength will reduce, and that is what we wanted. If the wavelength is reduced, then we can have the reduced size of the antenna. So let's say to illustrate this, let's take an example uh, of a signal working on a 10 kilohertz frequency. So if you are working on a 10 kilohertz of frequency, then your lambda, which is the wavelength, will come out to be 30 kilometer. You can use these values, 10 is to power 8 meter per second upon 10 kilohertz. So this will come out to be 30 this will come out to be the wavelength will come out to be 30 kilometer, and the antenna size will be 1/4 of this wavelength, and this will be 7.5 kilometer. So we see that how the distance of the antenna has been reduced drastically with the frequency of 10 kilohertz. 10 kilohertz. So, and previously we had 1 kilohertz, and with that the size of the antenna was 75 kilometer, which is 46.6 miles. And let's work on another frequency, which is maybe 150 megahertz. 150 megahertz. So this lambda, you will use the same formula, will come which will be 3 into 10 to the power 8 divided by 150 megahertz. So if you'll use that, then you will get 2 meter, which is really small, and the antenna size will be lambda by 4, which means this will be 0.5 meter. So you can see how drastically the size of the antenna has been reduced when you have increased the frequency. So this illustrates that how we can reduce the size of the antenna by increasing the frequency. Now here few key things we need to remember. First, the radio frequency range is from 20 hertz to 20 kilohertz, and normal people which are from 15 years or above, they have difficulty hearing anything over 15 kilohertz. Now coming back to the second problem which we saw in the previous slide. Interstation interference. So here imagine that somehow practical antennas were invented to work at audio frequency. We will want to operate several stations at the same time. So in that case, all stations will be sharing the same frequencies. It will be impossible to separate different stations at the radio receiver, since they all are on the same group of frequencies. So to to remove that to remove this problem, what we need to do is modulation. And there are three ways of doing the modulation, which is amplitude modulation, frequency modulation, and phase modulation. Let's first understand what is modulation. Modulation is the process of placing information onto a carrier frequency by using modulations. There are two advantages of that. First, antennas become shorter because of the radio frequency carrier. Second, separating stations becomes possible because each station uses a separate carrier frequency. So here you see by modulation our two problems which were there in the simple radio system have been resolved, because here we see with the help of modulation our antennas are shorter now, and also with that we are able to separate stations, and these could be possible only if we do the modulation. We will learn about the amplitude modulation, frequency modulation, and the phase modulation in the next coming lectures. Now let's understand this modulation and detection and this block diagram which is presented on this slide. So our practical radio system, which is consists of components like this, which is shown over here. So every radio transmitter is assigned to operate on a specific carrier frequency, and the job of the carrier oscillator here you see, which is connected to the modulator, is to generate this frequency, a carrier frequency. It generates and it is sent to the modulator. This carrier oscillator basically converts the DC from the power supply. There's a power supply is also connected, which is not shown over here, and it basically converts that DC power supply to AC signal. The output of the carrier oscillator is a nearly pure sine wave. The two inputs you see here, which are going to the modulator. One input is the RF, radio frequency sine wave, from the carrier oscillator, which is coming from here, and the other is the information signal, which is coming here from here. So you see here the microphone is attached and a voltage amplifier is connected over here. So from here the message, which is basically our information signal, is sent from this microphone, and since we know that the signal magnitude is very small, and that's why voltage amplifier is connected here, so that the magnitude can be increased, and then that signal is sent to the modulator. And here the job of the modulator is to combine a carrier signal, which is getting from here, with the information signal, and the output is modulated carrier wave is produced. So a modulator output which is produced here is too small to cover any significant distance, and that's the reason radio frequency power amplifiers are used, and which help in amplifying the signal. Now here, if you're working on a digital communication, so these elements will be a little bit different. In digital signals, they can't be directly sent over a long distance. Long distance digital communication usually requires that the computer's digital signal be converted into analog form from transmission. So that's the another thing to consider if you are working on a digital communication. So now here the second block diagram you see here at the bottom is for the receiver's side, and this is the practical receiver. So this receiver basically reverses the steps taken in the transmitter, and you can see how these components are basically the same thing but in the reverse order. Starting from here, this is the antenna which will receive the signal, and then we have this band pass filter connected over here, and the purpose of this band pass filter is to reject frequencies above and below its designed frequency. Most receivers, they usually uses LC resonant circuit as the bandpass filter, and one such example is shown here, of a LC filter. There are thousands of signals now reaching the receiver's antenna at any given instant, and yet the receiver must reproduce only one of them. So that is the main job of a receiver antenna, to pick the frequency which on which it is required to work on. And because these each incoming signals has a different frequency, it is possible to separate them by using a frequency selective circuit, and that's why we have this demodulator you see here. So which means we use a filter to do the job of selecting appropriate frequency, and that filter is basically connected over here in the demodulator. And demodulator takes the incoming modulated carrier waveform and strips away the carrier frequency, and leaving a copy of the original information signal, and which is sent through again through this power amplifier and then to the speaker. So here this audio power amplifier and RF amplifier, their main purpose is to increase the magnitude of the signal, and that and then in main message or the information is sent through the speaker, and from here we can basically hear the actual information. Now what happens in the radio transmitter? So these are the same things which we saw in the block diagram. I'll just quickly read them. Carrier frequency generator, we have already discussed. It is a radio frequency oscillator which creates the carrier frequency. Each radio transmitter uses a different frequency. Modulation. The desired information is impressed upon the carrier using AM, FM or PM, where AM stands for amplitude modulation, FM stands for frequency modulation, and PM stands for phase modulation. RF power amplification, where RF stands for radio frequency, and this power amplification, it states that the resulting modulated carrier is amplified in preparation for radiation into the space. Radiation, the transmitter's antenna system converts the radio frequency electrical energy into the radio wave, which travels through space to the receivers. What happens in a radio receiver? And these are some other quick things we need to see. Signal acquisition. The receiver's antenna converts the radio wave energy back into the electrical signal energy. So here our signal acquisition is basically the signal which we receive at the receiver side, and that is basically called your acquisition of the signal. Selection. The receiver selects the desired carrier frequency using the bandpass filter and rejects all others. RF amplification. The received signal is very weak and must be amplified before it is processed. Detection. The information is recovered from the modulated wave. After detection, the recovered information can be used as desired. So this is the end of this lecture, and amplitude modulation, phase modulation and frequency modulation we will discuss in detail in the next coming lectures. Thank you for watching this lecture.